For example, the bank stock data frame has a two-layer level of column. The first column we'll call the bank ticker, which we define it right here. Okay, bank ticker and stock information. For each bank ticker, for example, Bank of America, Morgan Stanley, Citigroup, and so on and so forth. And each one of the column, they have a sub-column as well called high, low, open, close volume, and adjusted closing prices. So if you just refer to the closing prices, and actually each one of the ticker has their own closing prices. So that's what I mean. They have a two-layer of column name. So in order to access sure. That's all about to say. Just say. This is coming right now. So here, if I want to access the bank stock, okay, and I want to access Bank of America, then I want to access their closing price. Understand what I'm trying to say? Or you can do bank stock, BAC, understand what I'm trying to say? You can using a so-called column name specification and saying it is Bank of America and closing. And the other one you can using an object-oriented, just .bac.close. Yeah, the same. Am I answering your question, Jack? Then you're using iLocation or location. Correct? So you can using location, and then what is it? 2010, 2012, January 1st, something like that. We'll show you some other example down there. Okay? So after defining the data frame, easy, we can actually go about the Panda data frame.xs is a way to access multi-layer of a column, either column or index. And some of the data frame you're going to see in homework 3, they will have a two level of indexes. Okay. And this example, you have a two level of column. So either way, as a row or column is the same thing. But here we're dealing with column mostly because each column represents different ticker, different type of information. And first level is the bank ticker. Second level is the stock information. So-called .xs is giving you a key, which is what? Now I want all the closing price. X is equal to 1, meaning I want column level, not the row level. And the level I want to referring to is in the stock information level. So this is stock information level. So then I perform a max. So it gives me all the maximum prices for closing prices for different type of stock. Okay, same thing. Here we can calculate so-called return. Okay, the return equals to the changing in price divided by the price for the previous day. So the price changes divided, then this pretty much we call it return, stock return. If this is negative, meaning today's prices is lower than the yesterday's price, so this number will be returning a negative return. If today's price is higher than yesterday's price, this number, the return will give you a positive number, and we can actually, using a Panda data frame as well, called percentage of change, it will automatically calculate that. You see the first row and didn't have any number, and rest of them is calculated. And this is very similar to row, what we call it, moving average. We using the first day as time 0 and everything, the second day's price minus the first day's price divided by the first day's price, and we call that stock return. And this term is generally used in in the financial sector very often. The next we take a look at the pair plot, and the diagonals show you the historical price of each one of the data, and also off diagonals show you a so-called cluster plot, and basically show you the correlation between the Bank of America to, for example, Citigroup, Bank of America for Goldman Sachs, and so on and so forth. You can see that for this example, it's not a very good example. They are all very much so-called positively correlated because they belong to the same sector. They react to the market in the similar fashion, which is a positive correlator. And you probably can vaguely tell the Wells Fargo stock is a little bit different from other bank stock, because Wells Fargo usually runs a very different operation than the other banks as well. Their investment, their hedge over risk are very much different. But still, they are the same sector of the stock data. They're almost the same. In this case, we can see that trying to give you the so-called return, which day the stock price is minimal. It shows you which day they are minimal. And Bank of America's is actually their minimum is in 2011, and most of the others, except the Goldman Sachs, dropped significantly on March 16 of 2020. That's when U.S. closing down for COVID-19 situation. And also want to see the maximum return for the index of MAX, which means maximum return on the historical. Actually, as majority of them is during the initial stage of the COVID closing down of the market, travel, and work from home, everything. It has a huge impact on the market. But you ask me, why is all the downs and up, the minima and the maxima, happens approximately in the same period? And actually, that means during that period of time, actually, the market has a volatile. So it drop one day, the next day, people buying it. So you have a heavily trading and buy and sell activity going on in those period of time. The next things we go over is a so-called standard deviation of the return. The standard deviation of the return usually referred as a risk, because the standard deviation is bigger, means the stock going up and down quite often and quite large in magnitude. So we call that risk asset. And for bank, they are usually very small. They usually like 100 point. 100 point means down to 1% and so on. But here, as Citigroups or Morgan Stanley are the most risky, but they're almost the same compared to the others. So the bank, the bank stock usually are not very volatile. But if you look at it at the Tesla, or especially if you look at the so-called Bitcoin, then they have much risky return on this. So this is a very frequently used the gauge in a lot of fund managers, mutual fund manager. are looking at for the risk assessment. Here I print out some of the return, and I also show you how to, getting the return standard deviation for specific time range. I think in the homework assignment I asked for 2015, but here I illustrated 2019, about the same. Distance plot, distribution plot, I'm sorry. I'm still using the location between 2019 and January 1st, 2019 to December 31st of 2019, and I only want what the Morgan Stanley's return. Notice that the return data frame is a single level column name, single level index, so I can directly call the column name. So the first bracket, square bracket, represent the row I'm selecting, or you can use using a Boolean condition to select the row, and then Boolean condition to select the row, and the next bracket represents the column. Same thing for city groups between 2019 January 1st to 2019 December 31st. See, the format I'm using actually be consistent with the index format as well. So if you have a different format of index, they can still handle it. For example, usually you're using for January 1st, month, day, then years. And then you have to use differently over here, slightly formatting. Question for me so far. And the rest of these are just plotting. Okay, plotting. And for this, I'm using a for loop to plot all the closing prices. I'm using a for loop rotated over the ticker. Tickers are all the stock symbols using, and for loop them through. And I first introduce the column, then I'm first layer of column, second layer of column, we call it multiple layer. So first layer is Bank of America, Citigroups, and Goldman Sachs, Morgan Stanley, and so on, JP Morgan, and so on and so forth. And I'm specifically going to stock information for the closing price. And I'm plotting out. Same thing over here. I can use an access to access them instead of a for loop. Okay, I just want to close price at the stock information level, and I plot them. This is actually slightly faster than the for loop, actually much faster. And I can also using iPlot from Cufflink to give you a live plot. So these you're using for stock price presentation, and this price data actually go on the minute basis. You can download them live if you are a paid customer. For example, you have trading account with a stock trade, a merge trade. They provide you minute to minute, up to minute level of stock prices, and you can plot them live on your website, and people can just view your website. But you say, oh, Dr. Wu, these are the stock data. Can I do this for production line or for logistic application? Where are all my trucks located right now at this moment? Where are they located in the next hour? When can I expect my shipment to come in based on the real-time data? Okay, we have a graduate working in JB Hunt and using Power BI to download these type of real-time information to track all the boxes for container boxes where they are located in different clients' parking lot, so they can resource them where they send it to haul another batch of a shipment. So these type of things can be applied not only for financial data, and actually these type of things we ask you to do is, here the cufflink originally is by default is online. You generate these plot online in a website. You can always refer to a web address and to display in your website. And so your managers or your people, your team can watch the location of your truck, your shipment on the live database. Next one, I'm doing the very similar with the rolling average, and basically it's the moving average for the 30-day period. Okay. Correlation chart, this is what we call the heat map, is using correlation of the data in the closing data. We're still using XX. And it shows you in the diagonal, they are all 0, 1. And the off diagonal, you see that if I zoom in a little bit. And you can see that they are actually 91% to 95% correlated, which means they have 90-some% of the correlation. And 1 means 100% of correlation. If it's negative, they are going, their correlation is opposite direction. But you can also tell the Wells Fargo has a far less correlation than every other stock, because Wells Fargo running a more conservative type of operation, so as opposed to other type of bank. Same thing, the heat map with the layer cluster map, and then can show you where the most correlated and where are the least correlated. Okay, so candlestick data, I'm showing for 1 year, but if you zoom in, actually they have a so-called high and low, and then they show open and close for the day. So green means going up and red means going down, basically. And these are actually small, simple moving average for 13 day, 21 day, and 55 days. And you see that the longer the day is, actually the smoother is the forecast. The shorter the period, actually they are more volatile and tracking the stock trending more closely. All right. Pretty much finished this. If no question, we're going to review the quiz number 6. Quiz number 6, we're using a data downloaded from Federal Reserve and St. Louis Bank, Federal Reserve, and for 1990 to 2021, January, and I can download these. What can you do is look at the data itself is monthly data, okay, and by the starting of the month. So here I'm setting the frequency of my index. I'm using the date as my index, and I'm explicitly setting the frequency to MS. MS stands for month, starting day of the month. If you're using only M, that implies the end of the month, which is January 31st, February 28th, December 31st. So MS is the starting day of the month, so you always see 01 as the ending portion. You can plot them easily. Okay, you can plot them easily. Then we can perform a so-called simple rolling moving average, okay, for windows of 12 day. Okay, since it's a month, I'm actually it's a yearly smoothing. And the second one is second one is doing regular weighted moving average, okay, for using time span of a 12 month. So we're assuming there is some kind of pattern going on in every year. Okay, so seasonal pattern is 1 year, and using simple smoothing average. But here I'm only using the column because each fit I'm adding a column to this data frame DF. Okay, so originally this data frame only have one column, which is the energy index. But now simple moving average is exponential smoothing average, and then a triple exponential. We start adding columns into this data frame. So I need to very much specify which column I'm using for as the input data. Okay. So simple exponential smoothing, I'm using the first column called energy index. And these are just copied directly from the forecast 1 notebook. And here I'm specifically using a smoothing level of, which is an alpha value for the exponential smoothing. And you see that it goes very smooth, and the green line actually is the forecasted data. And if I using equals to 1, actually it will match exactly the the curve. So lower the smoothing level actually give you a more smooth forecast. If this smoothing level, which is alpha value equals to 1, you basically trust exactly the previous data from the previous period, and then you will match the historical data exactly. Okay, but this will not help for the forecast into the future. This is just historical data fitting. So you can play with this at 0.2, smooth level, 0.2, 0.3, 0.5, 0.7, and you'll see the different result from here. I'm just illustrating one of them. So any one of those you will work. But if you don't specify anything, okay, if you don't specify anything, and the simple exponential smoothing will automatically optimize to find out what is the best level. And the next one, doing the triple exponential smoothing using the, here. Okay. From step models, TSA with time series analysis, Houghton and Winter, I'm importing the exponential smoothing. But this case, I have a trend, I have a seasonal, I can add a damping, and the seasonal period assuming to be 12 months. And I'm setting up the model like here, okay? And we'll call it fit number 3, and fit number 3, and we're getting the so-called fit value based on this model. It will fit the model and give you a forecast of fit value. And I call it added to another column in the data frame called TS multiply. Since I'm using multiplicative model, and you can using additive model as well. They're clearly explained in forecast 1 Jupyter notebook. So I'm going to see very close tracking with a seasonal effect. Okay. And actually finally asking for a specific range from 2006 to 2011. All I have to do is take the original data frame, which is the result, and using location function 2006 January 1st and 2010 December 1st. And that gives me similar plotting for the data frame. All these are various method of forecast method, and you can see how well they do compared to the original data. The original data is the blue line, all the others are forecasted value. Or I can using iLog, okay, using specific number, I backtrack for 180 to 130, approximate the same range I have. Finally, I want to show you a function. It's not part of your quiz, but I just want you to do a so-called decomposition plot. Okay, so you showed up using a seasonal decomposition function, and you plot the decomposition plot. Let me zoom out a little bit so you can see the whole thing. So this decomposition plot gives you the raw data in the first row. The second picture shows you the trend throughout these period. Okay, 1990 to 2020. And then show you the seasonal pattern. You know there's significant seasonal pattern. There's a kind of trend for level. Actually, it goes higher. And the final give you a residual plot. You can, based on the residual plot, you see how well the model was fit. And if I take off the trend information, take out the seasonal pattern, and actually we can see these are pretty random picture. If it's not well explained by these two factors, and in the residual you will see certain patterns still showing up, either kind of up and downs like a sine wave, or they trended in a certain direction. Okay, this is pretty much the quiz number 6. Any question about quiz number 6 before I move forward to talk about homework 3? Okay. Homework 3 is, it can be separated into two parts of challenges. The first, I download the car sales data. Okay, what do I have? I think I have from 2005 all the way to 2021. Okay, both. And then for each monthly sales, but you can probably tell from here, actually, this data is not in the similar format as we used to have a time series data. This is more in the Excel format of rows and columns. Rows represent each year, column represent each month. So how can we convert this data into a time series data? So I wanted all the data into one single column, and they are indexed by the month, years, and the month. So I'm using the index and the column as the future new index. And also you probably noticed that, I don't know what happened when I downloaded from this location, they give you extra column in the back, actually probably a new line character return and describe as not a value. So first couple things, I want to delete all the delete this column. We'll call it unnamed column 13. And also, if you pay attention to the data in 2021, even I have a value for January and February, but they are significantly lower than the other month I have right here. So they probably are incomplete data, which means some of the people haven't reported complete. A similar situation for COVID-19 positive case, death, and hospitalized information. So I decided to delete the last row and the last column here. So I'm dropping the column, okay, and so now everything I have. And then also I noticed that in these number I have these comma in between as a part of the financial data always come with it. So I need to first get rid of all these comma in the table and convert them into the integer or floating point number. So if you look at here, all the number I have, they are objects, which means they are string. Okay, and they are string data. So we need to convert them into floating point number. So I'm going to first replace all the comma with nothing, just no space. And I'm going to reset the type as a floating point and divide it by 10,000. 10,000, okay? And this is the resulting table, what I have, okay? Now all the data compared is kind of clean up. I can drop the last column, last row in a minute, but they are in the numbers format already. Okay, so another thing I do is using the Panda data frame stack to frame type of function and convert them into years and month. So 2 columns. So I'm using the year as the first index, using the column name as the second index. So once again, you see the index now have 2 levels. One level is year, the other level is month. Okay, the other level is month. So after the converting, you can see that I have 1 column called years, 1 column for month, and then I have all the data. Before I do anything, I'm going to eliminate all the data from 2021. So I'm setting a dropping all the row if they equals to 0, cells equal to 0, dropping all the row if they cells is less than 74. Okay, 74,000, and drop them. And I'm organizing the years and month, combine them together as the index now. Okay, and now you can see that I'm setting up, then becomes, you know, year, month, day, which is again starting of the month. We need to set the frequency equals to that. So after this is done, okay, I save all the information called autocells2.csv file, and then I will pursuing for the second part of the analysis. So this first part is kind of I intentionally using these Tableau format type of data. So you need to exercise how to convert Tableau type of data into a time series data, how to combine year information and the month information as a part of the index. Okay, so those things, these 2 columns are currently objects, which is a string. After you merge these 2 strings together, and you need to convert them into a 2-day time. So these are the things you need to consider what to do. And then we reset the index as a day, month, as a index name. Okay, so I want you to start exercising this first part already. And it's not too difficult, and but you have to start trying. This is a part of exercise for Panda data frame and different manipulation. But I want to tell you, as a data analytics, 90-95% of time, you are spending your time to massage the data into the format you want. Actually, the analyze, I already have all the references in the Jupyter notebook. Mostly you just copy and paste, correct? Those functions. So you really don't need to do a whole lot of, in the past, I have to explain the algorithm and takes a couple semesters for you to learn. But really, what you have is you can spend more time massage the data and using the existing algorithm to analyze your data. So for now, these type of things are so-called time series analysis type of methodology. And next week, we're going to go into machine learning. So hopefully we're using a different set of tools to analyze the data like this.